We have Ganesh from LinkedIn. We talk about learning to rank search result. Before we go, if anyone has announcement to make, I'll just open up the floor.
Hi everyone, my name is Junny Hu. So I have organized some event before here and also gave some talk. How many of you have been to my talk or events? Sure, and great. For those of you who don't know me, I currently lead the data mining team at Samsung, and before that I lead a team in PayPal on data science. But in my spare time, I'm organizing a big data association for Silicon Valley people. And we are exploring a new format of connecting people who are interested in learning about data mining. So I want to do a quick survey. How many of you are from business side? Okay. So most, I guess the rest are all engineering side. So the purpose for the organization is we want to connect people who has experience with people who are learning, who want to learn about, who want to get some guidance from people who are already in the industry. So I'm starting a new format called a mentor-mentee session. And I want to start, basically we can schedule time after work hours, say from 6:30 to 8 or 8:30, and connect you with a mentor to ask questions. The mentor may be allocated 30 minutes each time for answering, and you prepare 3 to 4 questions to come to the session. So that's what we are trying to explore. So talk to me if you are interested to to connect with a mentor, ask questions. So I will be sitting in the back and talk to me after the talk.
Anyone else? Okay, so we proceed with the talk. Hi everyone, I'm Ganesh. I'm a software engineer at LinkedIn. I work on search quality. When we were communicating earlier about organizing this talk, we had 2 choices, either this Friday or next Friday. I wanted to make it sooner, but I didn't realize that it was the Friday before the long weekend. In spite of that, I see a reasonable amount of crowd here, so first of all, thank you for coming. I will make sure that you learn something useful out of this talk. With that, let's proceed on. So the first thing you do before preparing for your talk is to know your audience, right? Because you need to tailor your talk for the audience. And we being data-driven folks, I started with the problem of audience classification, right? So I wanted to classify the audience, that is you, into 3 categories. People who have search background, machine learning background, search and machine learning background. Now, before describing my algorithm for classification, show of hands, how many of you here have a search background? Okay, that's 10-15% of the audience, roughly. Okay, so my classification algorithm worked like this. I took 15% sample from people who signed up for the meetup. I went to your LinkedIn profile. So if you mention machine learning in either your title or summary, I count that you have a background in machine learning. If you mention search somewhere, I counted that you have a background in search. And the algorithm was a little bit smart because it knows that information retrieval is same as search. Data mining is related to machine learning. So all these were accounted for. And this is the data. So about 65% of you have background in machine learning, 25% in search. And interestingly, everybody who had background in search also had background in machine learning, which basically told me that pure search but not machine learning folks are not here, at least from my sampling set. So based on that, I tailored the talks. Here's the overview. I want to present the search overview, not just because 75% of you, according to my classification algorithm, don't have a search background, but in order to understand machine learning, you need to understand the problem first. You can't just directly jump into the equations. So I'll talk briefly about learning to rank, LTR. The biases involved in collecting data, very important. What are the three basic approaches and the key takeaways and summaries? If you belong to the 25% bucket, with search plus machine learning, I almost guarantee you that you will also have something new to learn from this talk. If not, catch me offline. I'll make sure that you have something. Right? So it looks like on the internet, if you're publishing either your blog or slides, it's almost banned if you don't have a TLDR. And TLDR, for those who don't know, is too long, did not read. And I made sure that the number of characters is 130, so it fits into a tweet. So every slide in this presentation has got to do with one of these three aspects. And these are the three aspects that I want to drive in. One is that ranking interacts heavily with retrieval and query understanding. You cannot just throw a problem at ranking model and expect magic to come out. It's not going to happen. You will have to work with understanding the query. You will have to work with the retrieval system. The second point, I stole it from Airbnb blog. It's not theft because I cited it. So the ground truth is much more important than features. Features is much more important than model. As engineers, we all understand this, but when we start to wear our mathematician's hat, we tend to go towards the model part and ignore the ground truth. There's also some rationale towards it because getting ground truth might involve data janitor work and most people don't want to do it. But the fact remains that in terms of impact, if you want your model to work, you will have to focus on ground truth. And I'll tell you some of the gotchas in the ground truth as far as search is concerned. The third one is that list-wise models are better than pairwise and pointwise. If you didn't know what list-wise or pairwise is, I'll explain to you with simple examples. The model complex, this is in terms of performance, in terms of results. In terms of model complexity, it's the other way around. Pointwise is the easiest and followed by pairwise and listwise. I'll revisit this TLDR at the end of the presentation, but pretty much every slide focuses on one aspect of this. So let's start off with a primer on search because I want to make sure that you understand the problem before we move on to describe the machine learning part. So when we talk about search, we think about a user who has an information need, who keys in a query, which goes into a massive server farm, and results are being shown. But the true picture is that there is a lot of work done even before the user enters the query. These are system level tasks to make sure that the documents are properly indexed, retrieved, etc. So the real picture is something like this. You have quite a bit of system level work, which involves information retrieval. And then when you type in the query, you use this work to retrieve the results and rank. When we talk about search, it's easy to conceptually understand by treating it as pre-retrieval, retrieval, and post-retrieval. Pre-retrieval involves getting the input query, rewriting it if we need to, checking for spelling errors, etc., and then hit the corresponding search backends. Retrieval is simple. Given a query, give me all documents that match the query, also give me the score. And post-retrieval involves, typically search is a massive distributed system. Post-retrieval involves taking results from all these verticals, all these search nodes, merging them. It also involves adding metadata about the document, which are to be presented to the user, and giving it to the front end so that it's displayed in the right way. Let's focus on each of these aspects. But before we move on, let's take a small digression to Alice in Wonderland. So this is a very popular scene from Alice in Wonderland where Alice wants to know the way. And the answer from the cat is very simple but very thought-provoking. If you don't know, if it doesn't matter, if you don't know where you're going, any road will get you there. And this thought-provoking answer motivates the first claim, that search is about understanding the query and understanding the user intent. If you don't know what the user wants, there's no point in processing the query, and it's likely that you're not going to get good results. What do we exactly mean by this claim? Understanding intent involves taking the query and trying to see whether it's a title query, company query, geo query, etc. It involves calling the corresponding backends because a typical search system is organized into backends. In case of LinkedIn, that could mean a people search backend, a job search backend, company search backend, group search, etc. It also involves activating or finding the corresponding models. Each particular backend can in turn be trained with a different model. The example that I showed you here seems fairly obvious that software engineer is a title, Google is a company, and New York is a location. But there can be corner cases. Example of a corner case is Michael Dell. When you type a query called Michael Dell, do you really mean Michael Dell, the CEO, or Mike who works for Dell? So there is ambiguity there. So it involves a lot of these edge cases, focusing on a lot of these edge cases. It also involves fixing typos. Typos are very common in queries. It also involves spelling correction on names. Notice that M-E-Y-E-R, Mayer, is actually a more popular last name. But within the context of the user probably meant M-A-Y-E-R, Marissa Mayer. So it involves correcting these kind of issues. So a dictionary, normal dictionary lookup based on popularity of just the last name would be cut here. So that goes back to our first claim. So if you didn't understand the query or you didn't correct the query appropriately, it doesn't matter what your model is because you didn't retrieve the correct documents and you're ranking garbage. Now that motivates us to the second claim that search is about understanding systems. Search is a massive distributed system. Typically, a search index is organized into inverted index and forward index. An inverted index is a mapping from the terms to a list of documents. A forward index is the reverse. And each of them have their use cases. If there is one data structure that you want to understand about the search backend, it's the posting list. Conceptually, you can think about posting list as a hash table where the keys are the terms and values are the document IDs. Let's say you have 3 documents to index. Your corpus has 3 documents and the documents are as pointed out in the slide. So the term is an enumerated list of all terms in the document, and the posting list typically contains the document ID, in this case 0, 1 or 2. However, it can also have additional information like the frequency of the document, the frequency of the word in the document, which can be used for ranking purposes. It can also contain arbitrary payload information, like for example, in this case, what was bolded. So that information can be put in the posting list as well. Why do we need a posting list, right? So let's say you want a candidate selection for the query called Abraham Lincoln, right? As pointed out, your backend is organized in terms of posting list. In this case, we have a simple posting list which gets only the document ID from the query term. So you have 2 terms, Abraham and Lincoln, and your query has been reformulated to I want both terms to exist in the documents. So the retrieval is nothing but, in this particular simple case, it's a set intersection of 2 ordered sets, right? So some systems level issues, right? How do you represent a posting list efficiently? This is especially true for posting lists for terms that are often referred to as stop words, which are words like D and A, which are present in pretty much every document. So your posting list is going to become massive. Typically, the search nodes for performance purposes, the index is in memory. So all this information has to be contained in memory. So that involves a separate set of challenges. And why did we talk about retrieval? If you didn't do retrieval right, again, your candidate selection for machine learning is going to be wrong. Say your systems are down, infrastructure issues. Say you did a bad job with the posting list and the number of terms is large and it took a lot of times to retrieve and your master node which calls timed out. Or it didn't time out but it took a lot of time spinning the wheel for the user. All these can lead to bad user experience and hence retrieval forms a core part of search ranking as well. It interacts in a very deep way. That in turn motivates to our final claim, which is search is a ranking problem. We need query understanding and retrieval to make sure that we have the corresponding candidate set. Now let's say we do have the corresponding candidate set. How do we rank them? So let's start with what is search ranking. Ranking is nothing but finding an ordered list of documents according to the relevance between document and the query. So traditional search involves taking the query and the document, converting them into features, and getting a score out of this, right? Notice that often ranking is described as a function taking query and document and converting the score, but that's not right. Ranking is not converting into score. Ranking is actually finding an ordered list. There's a subtle but important difference in this. And we'll talk about these differences as we describe point-wise and pair-wise and list-wise approaches. However, this is LinkedIn and the user is important, right? So the function is actually, the score is a function of query, document, and user. Suppose I search for jobs related to Java. I live in San Francisco, so I expect the results to be around San Francisco Bay Area. I live in San Francisco Bay Area, and therefore the results should be around San Francisco Bay Area. Somebody in New York searching for the same term has to get jobs near New York. And this is just a simple example of how user forms a core part of the scoring algorithm. Why learn to rank, right? Why can't we just do, so we described the scoring as a function of query, document, and user. Why can't we use manual models, rule-based models? Rule-based models are hard to tune, and in traditional ranking, it may be possible to have rule-based model, but with an extra dimension, it's going to be really, really hard to tune as well as evaluate. Even data collection, getting the true data for a personalized world is harder. And we'll describe some of these challenges. But NTR does not come free. It also has some issues. It involves issues in how to collect training data, how to avoid biases, and how to train the model. And we'll discuss these issues in the coming slides. So what is training, right? So you have a set of documents for training, and you extract features out of these documents. You have human evaluated labels, and you get labels, and you just put this into a machine learning model. The problem is, this does not work in the personalized world. And the reason is the following, right? Usually, a user is shown, in order to extract labels, user is shown a bunch of queries, documents, and asked to label. Imagine that doing this in a personalized world. It's like telling me, assume that you are a nurse working in Dayton, Ohio, and try to evaluate these results and give a relevance label. It's very hard. It's doable, but it's hard. It's also hard to scale because when you have side-by-sides, another way of doing evaluation is you have two models and the user is shown side-by-sides, queries and documents, and a large number of such cases are shown to finally evaluate which model is better. Now if you add another variable called user, another dimension, it's going to explore the number of cases that you need to in order to make a valid decision. So we also have a large number of click data. So why not mine the click data? Let's assume that your query is machine learning and you clicked on this, which means that you didn't click on any and you did not click on any of this. So one simplistic model is that you can take clicked as positive results and not clicked as negative results, and then train the model accordingly, right? Can anybody tell me why this is wrong? Yeah.
The ranking dictates the probability that results will be clicked on.
Yes, that's correct. So the answer was ranking dictates the probability that the results are being clicked on. Or to put it in another way, the user scan goes in the order of the results, and then user probably did not even look at these results. So they are being unfairly penalized. The results below the click results, so there is a massive position bias. The probability that you click is dependent on the position that is being shown. And so this kind of simplistic model of data collection, though tempting to do, will not work. There's some literature background on this as well in the open literature. So there was two experiments conducted. The first experiment, Google search result 1, 2, and they looked at the probability of clicking the results. So the number one result was clicked over 55% of the time, and number 2 over 5.5% of the time. So you're tempted to believe that number 1 is far superior than number 2. But then they did the trick of flipping the results. And it's almost the same number of times people click number 1 and number 2. So if you had trained your model, assuming that your number 1 is far better than number 2, you're not going to get a good model. People trust results coming from the search engine, so blindly mining the click data and preserving that as the order is not going to work because of position bias. How do you avoid this position bias now that we said that there is position bias? Again, this is published literature. What you can do is take a small random sample and flip the results, right? You flip it, right? You flip the results, your relevance showed the Kevin Scott with the photo on top, but on purpose you flip the result, right? And then say the user still clicked the bottom result. You know for sure that the bottom result is better than the top result. Not all the top results, just the flip one. So this can be used as training data. It's called fanfares, it's a published paper, and that can be given as a training model, and this completely avoids the position bias. The second issue of collecting data is sampling bias. What is the best place to hide on the internet? It's Google result page number 2. There's nobody the fact is that there's massive decay on the click rate when you go from page 1 to 2 to 3. So if you were taking the results from your click logs, you're likely to take results only from page 1 or page 2. Therefore, your sample does not have the bad samples. It turns out that for those who have a reasonable background in machine learning, it's fairly obvious. But it turns out that if you want to classify cat videos, it's not enough that you tell that the machine that these are cat videos. You also have to tell the machine these are not cat videos. So if you're giving the click logs and you're basing completely based on that, you're not telling the system that these are bad samples. So you have a sampling bias. Now, how do you avoid that? You avoid that by assuming that one of the ways of avoiding it is that you assume your original search ranking is okay, right? Is reasonable, and you are trying to improve on it. If your original search ranking is okay, the 1000th or 2000th page result, which you never showed, is probably really bad results, right? So those can be used in your training data as easy negatives. Again, it depends upon your application. I just picked a random number as 1000, but you get the picture. You take an arbitrary tail result and you add that as negative data. Just to illustrate the point of sampling bias, let's assume that you did not do this, right? And you search for Hadoop. You notice that all the jobs that are shown are from San Francisco Bay Area. Assume that you have a feature which says, is the distance between the searcher and the job posted less than X months, right? Some reasonable X. Now, in your original sample space, everybody has this feature equal 1. Oh, yes, question?
Can you clarify more what you're sampling? Is it organic SEO search, or is it enterprise, or is this paid search? Not sure.
So the question is, what is your sampling based on organic search, SEO pages, etc.? It depends upon the application. So let's say you're doing people search in LinkedIn, it could be based on organic search on LinkedIn, search on LinkedIn, not coming through Google search. Does that answer your question?
Because the organic search may be different than enterprise search, or even if LinkedIn has organic search and also premium search. So it's two different search. So for the premium, is the organic search.
Yeah, so the models can be, so the question is LinkedIn has different search products, right? So there's a recruiter product, sales product, and then there's a customer search product. So they all go through different models. So the training could be different. Training data could be different. So going back, so if you had a feature that a distance between your searcher and the job posting is less than X miles, all these results are going to have that feature 1, and let's say it's a binary feature, 1 or 0. So if you put it in your model, what's the weight the model is going to come up with? 0, because the feature does not distinguish anyone. So, but does that mean that you discount geo? No, geo is an extremely important feature. So in order for that to happen, you have to avoid the sampling bias in any way. I'm not saying easy negatives is the only way to avoid sampling bias. It's one way to avoid. So an invasive procedure, there is actually an invasive procedure to avoid sampling bias. It is show bad results for a small section of users, right? But it's not good because you're taking a very bad results and putting it to the first page. So the non-invasive procedure is that you just assume that you have bad results in the tail results and add it to your sampling space. A similar approach can be used for easy positives depending on your application. If your application has a large number of negative data and you believe that this is sampling bias, you can add positives to your data. So how do you collect data, right? So there are two ways, right? Two big bullets. Is that you take implicit out of the search logs, you take implicit relevance judgments, and I'll talk about that. And then you add easy negatives. Relevance judgments. So say this is your click result, and I mentioned that you can't take clicked equal to 1 and unclicked equal to 0. So you can assume that, say you have relevance labels between 1 and 5. 5 being very high relevance and 1 or 0 being very low relevance. You can assume that the click result, one example, is that you can assume that the click results has the highest relevance. You can assume that the results that are above the click results, because the user eye scan happens from top to bottom. In this case, the third result was clicked. It's a fair assumption to make that the first and second were actually noticed because people tend to do that. And that has really low relevance. And then for those that are below the click result, where you're not sure whether the user noticed it or not, you can assign some sort of an intermediate relevance. This can be fed into the model, and I'll tell you how to do this in the model. So that motivates us to finally, how do you train the model? Now that we've talked about how you use query understanding and retrieval to get the candidates, how to avoid sampling bias and position bias so that you get valid data, how do you train the model? The first approach is pointwise. What is pointwise? Pointwise is, say you have training data which has a bunch of positives and negatives. You don't have relevance labels which are varying degrees. You just know that certain results are good, certain results are bad. And this is the simplest approach because you can apply any of the standard techniques. Then the objective is to find, typically say in an SVM based approach, is to find a separating hyperplane. And that separates the positive results from the negative results. There are a variety of loss functions you can choose. Logistic regression has a log loss function, etc. What's the issue with this? This assumes that relevance is absolute. And this alludes to the earlier point that I pointed out. Relevance is not about getting a score. Relevance is not something that is valid just for a document. It is relative. Relevance is relative. It's about finding an order, right? The other issue with this is that the documents associated with different queries are bundled into one positive set or one negative set, which also is not correct. So that in turn motivates us to the next approach, which is pairwise, right? In pairwise approach, your data consists of pairs where you're telling the model that A is greater than B, C is greater than 3, then D for a particular query. So query is bundled in. How do we get these judgments? It's the pair pairs approach that I detailed earlier, where you flip the pairs and you take it into the candidate set only if the lower result is clicked, can, for example, constitute a data set for pairwise relevance. And then the scorer is try to optimize a variety of things. One is, say, minimize the number of pairs where you didn't get the order right. The issue with this is, yes.
Do you do so give me a list of documents, do you do like an n-choose 2 pairwise, or you can optimize on because it's quadratic?
Good question. The question is, given a list of documents which we choose n-choose 2 pairwise, no, we cannot do that because prohibitively is expensive. There are better listwise approaches which are detailed. There is also a paper from pairwise to listwise which does tricks to avoid n-choose 2.
So let's say if I see like A is better than D, do I just say I'm going to, and B is better than C, then you say I just going to imply that A is better than C. So for those kind of situations.
So first of all, in the training data that I described in FatFast, we only flip one. There is, we don't have that data for the same query.
Okay.
Right? So that doesn't exist. That kind of stuff doesn't exist. Right? In any case, what you pointed out is a valid problem. If you do have relevance labels, right, then you can formulate it that way, but it exactly has the issue that you talked about, which it has n choose 2 and therefore it will just explode the sample space. There are tricks to be played to convert that n choose 2 to linear, and we can discuss offline.
Okay.
So there are ways to handle that problem.
Cool. Thank you.
So what's the issue with parallel approach, right? One is already, as pointed out, can read to n choose 2 if you train the data wrongly. The other issue is that it doesn't depend upon the position. So if 1 and 2 is wrong or 7 and 8 are wrong, you're giving the same amount of weights, which is not really true. Again, this is about ranking, finding the order list right, and it's agnostic to this issue. That in turn motivates us to list-price approach. In order to, the objective of list-price approach is very simple. You want, given a ranked list, a relevance labels for a particular query and a set of documents, you want to convert the entire ordered list into one scope. That's the objective. Instead of the formula, just think about it. Think about what the formula should. If you were asked to come up with a formula, what should the formula have? What property should the formula satisfy? If you got the first one right and second one wrong, and in second case you got the second one right and first one wrong, first one should have much better ranking than the second one, right? So there has to be a higher ranking for the higher order, and so which means that you have to discount for position, right? That's what this formula is, and I walked you through an example to understand the formula. I believe this is the only formula that I use in the entire presentation, and it's far less complicated than it sounds. What it means is that suppose you have relevance label for every document. So if you get the relevance label right, and higher relevance means better, you get exponentially better score. But that score is discounted by the rank. So if you get the 10th position relevance label to be lower, that's not as much penalty as first one being lower. So let's walk through an example, right? So let's say this is your rank list. You're searching for Java, and these are your list of results. The first one is a consultant, the second one is the inventor of Java, and the third one is a recruiter. And these are your relevance labels. You believe that James Gosling obviously has the highest relevance label, and your intention here is to find people who are good at Java, let's say, right? And these are your rank order results. Yeah.
How do you determine what is relevant and not relevant automatically by looking?
So so the question is, how do you determine if something is relevant or not relevant? Two approaches I described earlier. One is if you have fair pairs, where you flip the pair and make the one that ranked better lower, and if the lower one still gets clicked, you can use that as your training data, because that one is relevant and what is not clicked is not relevant. The second approach is that you can take implicit relevance judgments from the click results. So the click result is highly relevant. Anything above the click result, that is anything that was ranked higher than the click result, has poor relevance, and lower has some sort of intermediate relevance. I'm not saying, again, this is not the universe of choices, right? You can come up with something other than these, but these are some of the approaches to use. Okay, so using these approaches, let's say you have come up with these labels. Then you come up with the rank. So your first rank result has the relevance of 2, so it gets a score of 3 according to the formula. The second one has 2, 4.4. The third one has 1, so it has 0.5. So your total score is 7.9. And clearly, if you had got James Gosling better than the first person in the result, you would have gotten better score on this. So you have converted essentially a rank or a list with relevance label into a score. NTCG, if you look up papers, especially by Microsoft Research, have published a bunch of papers on learning to rank, and I have pointed to some papers in the end of the slides. You'll see them talking about this basic thing called NTCG. NTCG is nothing but normalized form of the DCG score that I pointed out earlier. So assume that you have a certain max score, And NDCG does nothing but dividing DCG by the max score possible. It makes sure that the score is between 0 and 1. Yes?
Excuse me, perhaps I'm the only one here. What does DCG stand for?
Discounted cumulative gain. Cumulative gain. So that's essentially a way to convert your ordered list into a score. And using that score, so since it converts a rank into a score, you can directly feed it into a bunch of algorithms like coordinate ascent, etc. And you can run it. And therefore you model the entire ranked list instead of modeling either pairs or modeling classification levels. So to summarize, we talked about 3 different approaches. What is pointwise? Pointwise is you're treating relevance as absolute, either good or bad, and then you're feeding it into a model. The advantages are that it is very simple, and simple does have its advantages, but it is query independent, and it assumes that, as I said, assumes that relevance is absolute, which is the From there we moved on to pairwise, where it does not assume that relevance is absolute. It assumes that relevance is relative because you're taking pairs instead of just points. It does depend on the query because the pairs are generated per query. It doesn't club every positive label into one category. But the loss function that you use typically is agnostic of the position. So if you got 1 and 2 wrong, or 9 and 10 wrong, they have the same weight. From there, we moved on to listwise approach, where we defined a certain function which captures how good the entire list is, so that function can be fed into a model. It models a problem in the way it's supposed to be, which is a rank ordered list. However, this is more complicated. It can become non-convex. You can turn it into convergence issues, but there are ways to avoid these. And they typically provide the best results. Again, there's open literature on this, why they provide the best results. I pointed to some of them in the slides. Yeah.
Is there a limitation to the length or the size of the list when you try to? For example, if you search for something really general, then there's like 1 million results, then or do you want to maybe only have the list-wise only sort for the first 20 results because that's going to be shown on the first page? You don't really care about it. Or do you want to sort the whole million result back?
The question is, what is the number of? Let me restate the question just to be clear. The question is, how big the size should be.
Yeah.
You only care about the first 2 pages, and you don't really care about the end pages. Now, so should you use the first 2 pages alone, or you use the first 100 or 200 pages, or whatever?
Sure.
Whatever the size is.
Sure.
Right? That's your question, right?
Yeah.
The answer is neither. So the reason why you certainly don't want to use the whole thing. You don't want to use the whole thing. It's going to really add to your computation time.
Right.
And the reason why you don't want to use just the first 2 pages deals with the sampling bias issue that I talked about earlier. If you have only the first 2 pages, it means that you're only giving the model good results. You also have to train the model with bad results.
Okay.
And therefore you have to take some tail results, assume that the relevance is bad, and then feed it to the model.
So you take the first 2 pages good result and you do a random sample of the bad results.
Yes, that's
So
one way of doing it. That's one way of doing it.
So you balance it. Okay.
Yes, so the one way of doing it is to take, the question was whether we take the first 2 pages and then random sampling of the daily results. Yes, that is one way of doing it.
Okay.
Yeah. So anyway, this goes to the 3rd bullet.
Why only take tail results for negative data? Why don't we take data which is not in the recall?
Not in the record?
Recall.
Oh no, you have to take results in the recall because then the features will all be. So the question was whether you take results that are not in the recall. And for those who don't have such background, recall is essentially what all documents match the query, roughly speaking. We don't take results that are not in the recall.
Not even negative ones?
No. So a fair representation is whether these are actually these results belong to the candidate set at all. And if something is not in the recall, it does not belong to the candidate set. Does that answer your question? So to summarize, we take training data from click logs, and train it into a model. We do offline evaluation and do A/B testing on online, and this is a continuous process. We keep doing it. While collecting the training data, we make sure that we avoid the biases and make sure that we have a reasonable sampling. That in turn leads us to the first slide, which was the TLDR, and I hope I drilled the 3 points, but I will restate them again here. Ranking interacts heavily with retrieval and query understanding. If you did not understand the query, did not correct spell check errors, did not call the correct backend, you're not going to get the correct candidate set, and therefore you're not going to get the correct results. Ground truth is extremely important, because, and you might be tempted to take ground truth based on purely on click logs. That will not work. You will have to actively avoid issues on position and sampling bias. The third point is ranking is about getting an ordered list. It isn't about an absolute good result or bad result, but a set of results. And therefore, list-wise is better than pair-wise, is better than point-wise. However, the complexity is in the reverse. The model is going to be more complex on list-wise. So these are some of the, if you are starting out learning learn to rank, the first paper is pretty good. It's a good summary paper from Microsoft Research. The material is easy to grasp and it is well written. Once you read the first paper, you should be able to branch out based on the references in the paper to whether a particular kind of learn to rank is interesting for you. The second paper is second thing is a book. The book is very comprehensive, so it covers a lot. I mean, the information that is present in the book, you should be able to find it in other papers, but it all puts together in context and puts together in one place. So the second book is, I read both the book and the paper, and I found it extremely useful. I did not know learn to rank out of school, so I learned to pick it up on the job. So these are some of the references that I personally found very useful. There's a library called Rankler. You can Google on this in the first click. You should be able to get it. It's a Java library that has a bunch of implementations of a lot of approaches that we talked about, list-wise, pair-wise rank, etc. It has a standard format for the training data that you can feed in, and it generates a model. It also does evaluation of your model, so it gives you numbers on how good or bad your model was, and it also provides routines where you can do this. You can use this online. So those are my recommendations. There might be better sources out there, but these are the stuff that I personally found very useful. Finally, that is the entire search team of LinkedIn. Search, as I told you, is I hope you have understood that search is fundamentally an intersection of information retrieval, distributed systems, as well as machine learning. So we do have a reasonably big team to handle the challenges. We are hiring across the board. So if you are interested in positions, not just machine learning, any other positions, you can shoot me an email, or if you forget my email address, I should be findable on LinkedIn. I hope this presentation was useful, irrespective of what your background is. And you can ask questions now or offline. I'll be around for some time. Happy to answer. Yes.
So say one aspect of search is you want to have some diversity. So if you look at federated search, so I'm just wondering if you want to throw in a diversity into the equation, how would you retrain a model?
The question is you want some diversity in search results.
Yeah.
So that's a really good point. Especially this happens we typically form queries as exploratory or navigational. So navigational queries are those where you want a particular result, in which case you want to get it right. Exploratory queries are you're searching for a job, etc. There are more than one result that are right. Especially in the second case, the diversity is a problem. You don't want to display jobs from one employer throughout. That's not potentially a good metric. There are ways to handle it. Diversity. You can bundle in the score and discount the score. You can take a level 1 ranker. Disclaimer. No, the techniques that I'm talking right now are generic. I'm not necessarily stating that these are used in India. So you can take a level 1 ranker, and in your level 2 second pass, you can produce a score for diversity. You have to be careful. Sometimes you're not looking for diverse results. Sometimes, say you're searching for jobs in Google. You do want jobs in Google, right? And then you can't discount Google jobs. So you have to be really careful when to use diversity. but it is an important point. And it is an important point both for diversity as well as ambiguous queries. So, for example, Wikipedia explicitly does disambiguation. So, if you're searching for Harry Potter, the last time I searched directly in Wikipedia, did you mean books or the movie, etc. Right? So, it explicitly does a disambiguation. But if you don't, you will have to make sure that you have both books and movies in the result set. Because some people they want books, some people they want movies, etc.
What percentage of LinkedIn traffic went to the based exercise? And
I couldn't hear your question, sorry.
what percentage of the LinkedIn traffic went through the pair exercise? And what was the percentage of traffic? Because you're swapping the results. Until what location were you swapping the results?
So the question was, what percentage of LinkedIn traffic went through the fair pairs? I cannot answer that question. Sorry. It was very, very small. So, yeah.
How do you do the evaluation?
One second, I think he had a question before. Your question.
Two questions. You mentioned in your example when you search for your
I can't hear you, sorry.
Oh, sorry. In your example, when you search for Hadoop, all the results were in a big area. So I wonder if there is manual logic based on distance to only show to the user like the people that are around on top of the search algorithm.
So the question is whether when you search for Hadoop in the Bay Area, the example that is shown, all results were in the Bay Area. The question is whether there was a manual override on top. Is that
Filter.
manual filtering on top? Again, I cannot go into specifics of what ranking we are using. I can talk in general terms, but there are ways to make sure that sort of behavior is met, even in an automated model.
So my second question is like if you guys are trying to do like a social aspect in the running side, trying to say like a recommendation on what your friends also search would be like an input to that learning.
I didn't quite follow your question. Is your question whether you are ranking based on what your friends or your connections searched? Mostly it's got to do with you. It's got to do with the searcher. Most of the features that we do are got to do with the searchers. Your connection is also taken into account, but how much I can't talk. You had a question? So the question is, how do you evaluate models? So there are a variety of techniques to evaluate, offline or online. Okay, so in offline, the NTCG number that I talked about, for a click result, you can see how much the click result went up. So that's a direct way of doing it, right? Online, you can always A/B test. So you have a control and you have a experiment to make sure that you have the correct sample sizes and test it. Yes.
For correcting positional bias, have you tried using the click-through rate, so dividing the number of clicks by impressions? And if so, do you have any thoughts on what the results might be?
We have taken the impressions into account, number of impressions into account in the model.
So the clicks that you're talking about already, that's already normalized by impressions.
Yes. So we do take care of number of impressions.
Yeah, so I had a question. So let's say I search for a term, right? And then I get a set of results. Then I search for a different, again, try to revise that. So maybe the first time when I search the results that I get, I didn't like it, right? So is there a way to account for that? The reason I'm searching for the second time is maybe the first time I didn't like the result. So how do you?
The question was, if you search for a term and then you reformulate it.
Yeah.
You reformulate and you didn't like the query, and then you reformulate it, and yes, we have put in thought into that. Yes. We have put in thought into exactly what you're talking about.
So is there any models like or some reference?
I have to look it up to see if there is anything in public domain that can talk about that, but it is, I believe I have seen something in public domain because I have explicitly searched for this, but I don't remember it offhand. I can sync up offline. But it is a very valid point that if you formulated your query then your original results may not have satisfied your information need, and that can go into the training data. Yes.
And one more question. So let's say I search for a term and then I get a list of results, right? And then I clicked on one, and then I clicked on one, then go to that profile. Maybe. So do you also take into account how much time I'm spending on that? Maybe the result that I clicked was not really the one I'm looking for.
So the question is, if you clicked on one result, you spend some time, or you don't spend any time, how do you take into account, right?
Yeah, and then go to the maybe next one, and I spend more time.
Again, I'm treading a very dangerous rope here, right? I cannot talk deeper into it. So generic questions like models, Linkedin is a pretty open company. We have open sourced a bunch of software. So we've also published results on related to search. We've given a bunch of talks. But the problem with search or particular features in general is that if we openly specify the features, it can be gamed. So we have to make sure that that is not done. I cannot talk about specific features. Yes.
A while ago, I saw you guys have something called dojo that you guys are building and selling, open source, but you practically stopped working on it, right?
Can you repeat which one?
Can you describe what is the current sort of the open source package from LinkedIn search? Like, what is the thing that you guys currently working on?
Sorry, question is, what is the current state of open source? We have open sourced a bunch of stuff related to search, Bobo, Zoe, etc.
Yeah, I remember Zoe.
Right. So we have the current stack. We published a blog on this. We're currently working on a new search stack, search backend, and we're testing it within LinkedIn. It's called Gaining, and we had a detailed blog on why we chose Gaining as our search architecture. I'm not sure about the open source status of Gaining, but that is how the direction of search is towards this new backend.
What's the coding?
It's called Gaining, G-A-L-E-N-E. You can Google on LinkedIn search Gaining, and we have detailed the architecture of Gaining and why we chose this.
How did you scale the LinkedIn?
How did you
scale the training of your work?
How did you scale? The question is, how did you scale? So there are distributed platforms available for machine learning. So the open source ones are things like Mahal. I'm not saying we use Mahal, but there are ways to scale machine learning platforms.
My question was specifically for LinkedIn. What did you guys do?
So for us, we use mostly open tools. So for the training search specifically, most of the offline training is in Python, and we used SciPy, NumPy, etc. Scikit-learn has a bunch of learning algorithms already implemented.
I didn't quite catch the practical benefit of pairwise. I got the practical benefit of pointwise and listwise, but pairwise has rather the relative relevance. What kind of method would help? That's my question.
So the question is, you did not catch the practical relevance of pairwise. You got the practical relevance of pointwise, right? So two parts answer to it. It's easy to generate training data because the fat pairs you can do it pretty easily. It is not invasive because you're taking, say, 7th result to 8th result and flipping it, right? And so it's not that bad for the user. So that's one way of looking at it. Pairwise is still you can formulate it as in reasonably simple models. Listwise, if you use MBCG, it is a non-convex function. So that's another aspect. In terms of debugging, if you have some pairs that are misclassified, it is easy to just dig into one part. Whereas in MBCG, you get one score for the entire list, and you have to debug why this particular score came into. So in general, the theme is simpler than one. It is simpler, and therefore if it works for you, you should just choose it. Anything else? Okay, thanks for coming. I'm going to be available offline. So